Large language models are fantastic at laying out the logic for complex structural problems, but if you ask them to calculate the precise load that will shear this gear assembly, they become a liability. To use these systems safely, you have to adopt a strict discipline of checking the work before trusting a single digit. The mistake we make is treating an engineering calculation like a single, solid block of work. It is actually a sequence of very different tasks. This visual breakdown splits a standard calculation into 4 distinct pillars. First is the conceptual setup, then bookkeeping. Next is numerical execution, and finally, sourcing your data. A language model's true strength lies almost exclusively here, in the first 2 stages. When you hand a model a loosely stated problem, it is highly capable of identifying the correct governing equation and drafting a clean list of physical assumptions before a single number is plugged in. It can handle the bookkeeping with ease, keeping track of units, running dimensional analysis, and rearranging the symbolic algebra into a solid first draft. Confining the AI to these early steps turns it into a powerful organizational accelerant. It frees you up to focus on the overarching logic instead of getting bogged down in preliminary formatting. But the utility stops abruptly when we reach the 3rd pillar. When tasked with plain numerical execution, the models consistently break down. Look at this mathematical chain. A tiny arithmetic error in step 2, common in exponential relationships, compounds into a massive final discrepancy by step 5. This happens because language models don't run rigid logic. They perform next token prediction, guessing the next shape in a pattern. Unless the system is explicitly connected to an external numerical solver or a code interpreter, it has no actual capability to compute numbers, and that lack of capability is hidden. The model will wrap its incorrect math in highly authoritative, fluent prose that never signals a mistake. Relying on an AI for a final computation is dangerous because an entirely wrong number reads perfectly to a casual reviewer. There is a second, even less visible failure point: the complete fabrication of empirical data and standard citations. If a model does not know a specific material property, it lacks the internal mechanism to stop and say, "I don't know." Instead, it invents a plausible-sounding value to fill the gap in the sentence. In high-stakes engineering, this hallucination is acute. The AI might supply a fabricated Nusselt number or an invented friction factor that looks entirely real, and its confident tone never changes. It sounds exactly the same quoting a verified standard or making up a constant. Fluency and factual correctness are completely separate properties. A system built for pure fluency will silently propagate critical design errors if those values are left unchecked. The practical response is not to ban these tools from the workshop. The response is to enforce strict physical boundaries around how they are used. First, mandate a total separation between drafting and computation. Let the AI structure the algebra, but generate the final number yourself using a deterministic solver or a hand calculation. Second, independently verify every single empirical correlation against a primary source, like a recognized property table or a handbook. Third, always run a manual sanity check. A quick order of magnitude estimate or testing a limiting case will immediately flag a fabricated answer. Finally, treat the model's apparent confidence or its lack of expressed uncertainty as completely meaningless. Taking a model's final output and pasting it into a design without these physical verification steps is an abdication of an engineer's core responsibility. We have reached a practical synthesis. Artificial intelligence speeds up the drafting, while deterministic tools and hard reference books secure reality. You can absolutely embrace the speed of the assistant, as long as you apply the rigorous verification discipline that the profession demands. To learn more about integrating these frameworks into a professional engineering workflow, visit our platform and read further.